Now that we've had a couple of practice examples working through z-scores with our examples, ACT and GRE scores, I want to cover just a couple of final things related to z-scores. First of all, some terminology that I want you to know. In our original question, we asked what is the probability of getting a 1.27 or higher. If you think about what I'm asking here, I'm asking for a single direction. In statistical sort of terminology, what I'm really saying is I'm only concerned about one tail of the distribution. So we could call this, if you wanted to, a one-tailed test. Okay, when I am concerned about only one direction of the curve of my distribution, that is a one-tailed test. Okay, and that's primarily the examples we looked at here. I'm only concerned about one direction. However, there are times, and most of the time as we move further into research, where we're not really interested in only one area of the curve. So let's think back to our original example that we talked about when we started all of these videos. Let's say I have a program that is designed to improve ACT scores. Well, certainly I am interested in this side of the distribution and seeing, okay, what is the likelihood of people improving? Okay, that's sort of the nature of that question. But at the same time, I would also be interested and would want to know, even though I am expecting my program to help, there is a possibility that my program, though well-intentioned, may actually hurt students, and they could end up doing worse. Okay, in that case, I want to be able to run an analysis that will capture both sides. So I'm hopeful that it will improve scores, but I'm also leaving room for the fact that maybe my program might actually hurt students. In this case, I am interested in both sides or both tails of the distribution. And in a question like that, we would call that a two-tailed distribution or a two-tailed test. Okay, so a one-tailed test, we're only interested in directional effects on one side of the tail. That could be either positive or negative, but I'm only interested in one side. With two-tailed tests, I'm interested in both directions. Okay, so let me give you sort of a practical example of how this sort of works out. Let's say that I am interested in finding out the extreme ends. I told you that we, in social science, like to sort of weed out, if you will, or be concerned with weird scores. Okay, and just for our purposes, again, let's say we're interested in everything outside of 2 standard deviations, plus or minus 2 standard deviations. Now, if you go back to our empirical rule, we know that what percentage of the population of scores does that represent? If you flip back to your empirical rule, and at some point you'll need to commit this to memory, we know that this is approximately 95%. So, plus or minus standard deviations of 2, we know captures approximately 95%. Now what I want to know is not the approximation value. I want to know the actual z-score, in other words, the exact z-score where I capture 5% of the population. 2.5 on the extreme end here, and remember, because this is a symmetrical example or a symmetrical distribution, mirror image, that whatever happens over here also happens over here. So if I'm looking at 95 in the middle, I want the 5% on the edges. So 2.5% on the positive edge, 2.5% on the negative edge. So we can draw this out. Okay, I'm looking for whatever this z-score is. Okay, I don't know the z-score, but I want this percentage here to be, or the probability to be 0.025. Okay, 0.025 here is then also going to be 0.025 here. Okay, now, one thing you hopefully will have noticed about our z-table is there are no positive and negatives. The reason is whatever you do to one side, you do to the other. So basically I could, if I'm talking about 5%, that's the total. But I can also do what I've just done, separate it out, and now I'm looking for the 0.025. If I find that value, that will be the P that's the positive as well as the negative. So, in case you're a little confused, let's walk through this example. I'm looking for 5%, 2.5% on each side. So let's find a percentage of 0.025 and get the corresponding z value. In other words, here's the question that I'm asking. What z value is associated with a smaller proportion of 0.025? So in this case, we're going to look at the chart in front of you, and we're going to skim down that smaller proportion column and try to find a value that equals 0.025. So if you look at that fourth chart there, or the fourth major column over, and we're going to look at the smaller portion, skim down there, and it's going to be near the bottom. In this case, it's highlighted for us, and I'll tell you why here in a second. But we see that the smaller portion there equals 0.025. Follow that out to the left just a bit to see what the z-score is, and what do we find is the z-score? It's 1.96. So let's plot 1.96 here. Okay, so this is 1.96. So now I know that everything from this direction over is a probability of getting a 1.96 or higher is 0.025. But that wasn't my original question, was it? My original question was, what is the z-score that captures 5% of the population? Well, whatever I do on the positive side, I also need to do on the negative side. So if a positive 1.96 gives me 2.5% over here, what value gives me 2.5% on this side? It's a negative 1.96. So I can plot that here. I shade in this area. And now here's what I know. I know that a z-score of plus or minus 1.96 or more extreme will give me 5% of the population. Okay, so I know out here plus out here is 5% of the population, which means what's in the middle? If this is 5%, now this is the 95%. So here's what you need to commit to memory. The empirical rule tells us that approximately plus or minus 2 standard deviations gives us 95% of the population. However, the exact value is 1.96. We know that plus or minus 1.96 standard deviations, or a z-score of plus or minus 1.96, will give us 95% of the population in the middle, 5% of the population to the tails. Hopefully that makes sense. If not, we will address this some more as we move forward in our face-to-face part of the class.